1, you can never get to C2H, no matter what kind of matrix you do. Okay, so so these two can never be conjugate operations. Okay, so that's basically all there is qualitatively. And if you manage to do that, figure out which one are conjugate to one another, you find that this 32 point group for crystal separate into 7 different classes or type. Okay, so these are the 7 different classes that you have. And you notice they are the standard one, the monoclinic, orthorhombic, tetragonal, trigonal, hexagon, and cubic, of course, that you see that we are familiar with from cubic. Of course, we learn about this in first year chemistry. And the other we may come across in group theory courses. So there are 7 classes of these. And sometimes they are also called lattice type. The class is also called lattice type. So depend, again, there's some inconsistency between each books that you read. So sometimes they would call lattice type, but they are classes. Really is a higher layer, another layer of mathematics that connect the group element to one another. Okay, so and this lattice type or group, so they are given some notation: P for primitive, C for center, I for inversion, and F for phase. This sort of thing. So you have lattice symbol P as primitive, which is when you have a cubic system. SC stands for simple cubic, and I with the inversion symmetry, you have body center cubic, right? And F with space symmetry, you have phase center cubic. So these are the things we learn about in first year chemistry. And in reality, this 7 group of elements connected to one another by these lattice axes. So A, B, and C is defined this way. A, B, and C are lattice vector, and alpha, beta, gamma are the angles between these lattice vectors. And they have connections. So even though mathematically you can do this fancy transform, but in reality, a more concrete way of thinking of classes or type or lattice type are really these restrictions, like definition, connection between the lattice vector and lattice angle that you have. So for example, cubic, of course, cubic A, B, and C are the same, and the angle, alpha, beta, and gamma, is 90 degrees, right? So that's clear from this. And of course, you can talk in fancier terms with the mathematician in terms of these conjugate transform and so forth. Within this group that you got, okay? And then you have trigonal, for example, A, B, and C are still the same, but the angle are no longer 90 degrees. They are 120 degrees. They are the same, but they are 120 degrees. Okay. So these are the rules, if you like, of building this trigonal lattice or lattice type or class or group class that you see. All right. So we are more as chemists. We know this, right? We learn about these in undergraduate. And here in a little bit more detail. From this lattice group, you can add this lattice group. In effect, once you define this lattice group, you can generate something called Buffet's lattice. So this is hard to define. Buffet lattice is very difficult to find a definition. It's kind of like this, right? This is the so-called Buffet lattice. So let me talk about in word first. So Buffet lattice is usually just a way to indicate the skeleton. Think of it as a skeleton unit cell, right? It's the skeleton of your crystal, right? It's indicate a distinct lattice type, which with restriction on the lattice parameter A, B, and C. So just like what we define for group, like this restriction, the relation among the lattice vector. And there are 14 of these Buffet lattice or lattice type, okay? And these 14 of these separate into 7 classes, just like what we had before, group into 7 classes. And we can think of these as skeleton 3D mesh or grid that when we combine a operation, translation symmetry, just moving one lattice to periodic spacing, you generate an entire crystal. Okay, so Buffet lattice plus translation will give you the entire crystal that you got. Okay, so we think of Buffet lattice like this. As chemists, we think about it like this, right? So you think about this is how we teach our first year student. Simple cubic, right, which is primitive cubic. Cubic eye was inversion symmetry, right, with the body center cubic, and then you have face center cubic with 1 point in the center, like this. And body center cubic, BCC, of course. FCC. Face center cubic is closest pack, what we call closest pack structure. And these, of course, the 7 type belong to these 14 Buffet lattice belong to 7 type of symmetry group, symmetry class, and here they are. Okay, and they're connected to each other by this transformation mathematically. Okay, so that's what we think about, and really that's it. So in some way, it's quite simple. You think about bulk symmetry. That's all there is. There are only 14. It's kind of amazing, actually, if you think about them. That nature only have 14 lattice type that generate, that describe the entire universe in this way. Okay, so these are Buffet's lattice and the unit cell they constructed. Okay, so these are point group, and then there are something called space group. Okay, so that's what we know. Something that we may not know. Some people may not know is space group. Space group, there are lots of space group. And what is space group? Space group are really additional. It's like you take your point group, all the point group symmetry element, and you add more to it. And you add, what do you add? You add symmetry element that lead to translation and object in space. Okay, so basically you add translation-related symmetry element to your space group operation, to your point group operation, and then you generate the space group. Okay, so it's a very elaborate thing. So you add additional symmetry element that lead to translation and object in space. Okay, and that's a qualitative definition of what a space group is. And this additional translator-related element combined with point group give the formation of space group. So actually that's the definition. And the certain symmetry group are not allowed because of this translation-related operation. And one interesting one that I point out here, is that you will never find a crystal with 5-fold symmetry in nature. So this is a no-no in nature, although we all have 5 fingers and 5 toes and things like that. So it's a kind of an interesting thing that crystal will never have 5-fold symmetry. It has 6-fold symmetry. It doesn't also have 7-fold symmetry. Very rarely you find them. It doesn't have infinite fold symmetry. Also, infinite fold symmetry means that essentially there's no symmetry, right? That's what infinite fold symmetry means. And in essence, what you got, the Buffet lattice define these restrictions with